All right, we talked a little bit about Thevenin's theorem, and one thing that it is really useful for is figuring out how to get as much power to a resistive load as possible. One of the reasons that we have circuits in general is because we want to get power to something that's resistive. So, if we have a resistive load and it's connected to a circuit, how much resistance would give us the maximum amount of power getting to that load and not just being dissipated in the rest of the circuit, because everything in the circuit is going to dissipate a certain amount of energy, and we want to get the most energy out to the resistance. And what are we going to do? So, first of all, we take any circuit that is being connected to a load resistor and we change it to its Thevenin equivalent. And then we're actually going to experimentally look at how we would determine what would have the greatest amount absorbed. So we're going to look at a circuit that has already been Thevenized. So we've already found the Thevenin equivalent, and we have connected a load resistor. And what we're going to do is look at this circuit and sort of remind ourselves of a couple of things. First of all, if we know the voltage across RL, which we can find really easily with a series circuit, we just use the voltage divider rule, which takes RL and divides by the sum of RL and R Thevenin, or RL and 10 ohms in this case, and we multiply by V Thevenin, which is 10 volts. That will give us the load voltage at any time for any value of resistance. And then to figure out the power, this time we're going to take V squared over R. We could have used the current, but we didn't. And basically we're going to take a number of values of resistance, running from 2 ohms to 20 ohms, and just tabulate what voltages and powers are related to that particular, to each value of resistance. So you'll notice that the resistor values here go from 2 to 20, and these are all in ohms. And then the voltage is just calculated, just using a spreadsheet for each one. You'll notice, predictably, the voltage increases as the resistance increases. That's what we expect. Then we take the value of the power, and we have tabulated that by taking the voltage squared and dividing by the resistance. And you'll notice that the power goes up, and then it reaches a point right here where it's at its maximum. Yes, those are how we calculated that. And then that maximum exists, and then it goes down because we've got the voltage squared, but the resistance is getting bigger. So that occurs at that value of 10 ohms, which is actually equal to the Thevenin resistance. If we were to take this data and plot it, you would see that the maximum amount of power that gets to the load is when that value of resistance is equal to the Thevenin resistance. And that's what the maximum power transfer theorem says, that if you have an independent voltage source, which would be V Thevenin in this case, with a series resistance, R Thevenin, it will deliver the maximum amount of power to a load when the load equals the Thevenin resistance. So the good thing about that is this is a really easy concept. Once you have the Thevenin circuit, the maximum power that is going to be delivered will be delivered when the load resistance equals the Thevenin resistance. There are two different ways to kind of present this as a problem. One is if we only want to know the value of the load resistance that'll draw the maximum amount of power from a circuit, then we just find the Thevenin resistance. We don't really have to do anything else. So if you have a very complicated circuit and you have a load resistance and you just want to know what the value of the resistor would be, you just find the Thevenin resistance. If you want to know how much power is going to be absorbed, then we might find the Thevenin voltage, but we could also use other types of circuit analysis once we know the value of the resistance. So you don't always have to make a Thevenin circuit to do these problems, but you do have to find the Thevenin resistance. That value is going to always be found. So again, we're going to look at examples. Examples are the best way to illustrate anything. And what we're going to do in this case is we have a circuit, and we're going to use Thevenin's theorem to actually find the value of load resistance that will absorb the maximum amount of power. So this is only asking for the value of the resistance. This is not asking for how much power or what the current is or anything like that. It's just asking for the value of resistance. So all we have to do is the resistive part, so far at least. It may change in a little bit. So we're going to remove the load resistor. When we take that out, we actually have a gap in the middle of the circuit. And then we're going to turn off the voltage sources by replacing them with short circuits. And we're going to look at the Thevenin resistance between those 2 points. And as you'll notice at the top of that node where the R Thevenin is being connected, there is a node. And then there's a second node that goes all the way around the bottom. All that encompasses wire, as you can see. And this means that the 300 and the 600 are in parallel when we are measuring the resistance at this point. And this is really important to keep this in mind, because it kind of looks like this could be just add the resistors, but this is not the case because of the perspective from which we're actually taking this resistance. So we're actually going to take the parallel equivalent of 600 and 300, and we get 200 ohms. So that is the answer to the problem. Use the Thevenin's theorem to find the value of resistance that would receive maximum power. However, what if we wanted to know how much power that circuit can deliver to a load resistor? So this would be a little bit of a different problem. This would be what amount of power could be delivered. So the first process that we would use, or the first thing we would do, we already know the value of resistance that needs to be in the place of RL. Then we don't have to find the Thevenin equivalent circuit if we don't want to. We just need to know how much power is being dissipated by that 200 ohm resistor right there. So the easiest thing in this case is actually to use nodal analysis. And there's only one unknown node in this circuit. There's VA, which is between the 600, the 300, and the 200 ohm. And we can put in some current directions, and then basically we just have to solve for one value. So the current coming in here, we've got two currents coming in. One is going to be 50 minus VA over 600 would give us this current here. We would have 30 minus VA over 300 would give us this current here, and then VA over 200 would be going out, and we would end up with this equation here, and all we need to do is simplify it. So the 50 over 600, the 30 over 300 are the constants, and then 1 over 600, 1 over 300, and 1 over 200 added together would be the constant in front of VA. And basically, VA has been moved to the other side to make it positive. So even though these, if we move the 50 over 600 and the 30 over 600 to the other side, that would be negative. But then we have 3 negative signs in front of VA. So that's why there's no negatives now, because basically VA was moved to the other side. So we get a value, a linear equation like this. We solve for VA, and we get 18.33 volts. Once we know that, then we can figure out how much power is being dissipated by the 200 ohm resistor, which would just be this voltage, which is the voltage across the 200 ohm, squared divided by 200. And we get 1.68 watts. This is the maximum amount of power that this circuit can deliver to a load resistor in the position that we put it in. If we had RL in a different place, then we would get a different value of power. But the circuit configured the way it is, and the load resistor in the position that it is, means that this is the maximum of power that that circuit can deliver to a load resistor as it is designed. So this is something that, again, is oftentimes we need to know this, and this is sort of how we do it. So just a basic summary, if we want to know the resistor value, we have to find the Thevenin resistance for whatever position that RL value is in. If we want to know the power dissipated or the current or the voltage for that resistor, then we can use a multitude of circuit techniques to figure that out. So we don't necessarily have to find the Thevenin voltage. However, if you're presented with a Thevenin circuit, then that makes it all that easier because it's just a series circuit. So there will be a, again, lesson that shows you a couple more examples of how these concepts work, and there'll be your usual homework assignment, and we'll see you later.